Welcome to the final presentation for the interactive cat toy projects. The members of Group 25 are two electrical engineering students, including myself, Bong Wing, and Elizabeth Vargas, and two computer engineering students, Joseph Lopez and Eliza Grabowski.
We are extremely thankful to have our sponsor working with us. Lei Fan is a mechanical engineer and author who notably worked with the mechanical design of the Avatar ride at Walt Disney's Animal Kingdom. He recently published a book entitled How to Design Mechanisms That Last a Lifetime, Practical Applications of Grouplers Count, and hosts a YouTube channel where he demonstrates methods from his book. Lei has generously given his time to take care of the mechanical design and 3D printing for our project.
It's estimated 373 million cats around the globe are kept as pets, with approximately 93.5 million pets here in the U.S. This provides for a large number of pet owners looking for toys to entertain their loving felines. Toys are a great way for owners to have fun and enjoy their time with their cats, while also giving them their needed exercise. But finding the right toy is the real challenge. Our senior design team decided to take this challenge and build the interactive cat toy.
Goals and objectives. With this project, we want to design an interactive cat toy that cats can be entertained by and engage in play with for hours. We also want to incorporate elements into our toy that are key to domestic cat entertainment. Work to implement the current standards and the best safety factors that we can. Also, we want to design our ICT so that it can withstand rough cat plays and last for a reasonable amount of time.
We performed market and product research to help us plan the design for the interactive cat toy. This research helped us to identify key features that were proven to entertain cats. We planned to incorporate all of the key features that we identified into the interactive cat toy, and we take our toy design further by adding control of select features to a phone application.
Key engineering specifications for the ICT are highlighted in yellow. We will limit the lighting intensity to under 10 lumens. Our whole system delay time for our phone application will be less than 5 seconds, and our motion sensor will detect motion within 4 feet. This is our hardware block diagram. Elizabeth Vargas is responsible for the battery charger, power supply, and the switch. Joseph Lopez is responsible for the mobile application and the Bluetooth module. Eliza Grabowski is responsible for the majority of the toy's component, which are LEDs, speaker, and motor. And I, Vu Nguyen, is responsible for the MCU with the PCB design and the motion sensor. For a toy, we have 3 hardware layers. The outermost layer is the interchangeable exterior skins. The middle layer is a protective chassis, and the innermost layer is electronics with the PCB and its components.
We decided to construct 2 interchangeable exterior skins for our interactive cat toy. The exterior skins are designed with the same measurements and a zippered opening so that the chassis can be easily switched between them. The chassis for our toy is designed to protect the electronics of the toy, to support toy features, and to be easily switched between the toy's interchangeable skins. The mechanical design and 3D printing of our chassis is being done by our wonderful sponsor, Lei Fan. Electronics for the interactive cat toy include our microcontroller and electronic feature components. All feature components for the interactive cat toy are RoHS compliant, ensuring environmentally safe products.
The main hardware components that we selected to build the interactive cat toys are listed in this table. Among microcontrollers, the RB2040 seems to be the best option for us to use with the interactive cat toy. For testing, we use Raspberry Pi Pico, which is the development board of RB2040. The specifications for RB2040, especially the amount of GPIO bins and the operating voltage, made it ideal for our projects.
There are many options out there for Bluetooth but the best recommendation is to use a module version 4 and above. We decided to go with the HM10 Bluetooth module, but the module we bought had connectivity issues. Though they claim to have iPhone compatibility, we could not get our iPhones to find the Bluetooth connection. We settled with selecting the HC05 compatible only with Android.
The speaker selected was Adafruit's Stemma speaker. It is small in size and has an amplifier built in.
We selected to go with the Tower Pro micro servo motor from Adafruit to facilitate tail motion for our cat toy. Servo motors allow for embedded code to use PWM to control positioning of the gears, giving us just what we needed to correctly simulate tail motion. This micro servo motor is ideally sized and has robust metal gears.
The lighting selection was the NeoPixel digital RGB LED strip from Adafruit. This is due to the WS2812 LEDs used.
For our motion sensor, we decided to use the PIR sensor. This sensor has an adjustable range and a wide area of detection.
Initially, we selected PETG to print our chassis, assuming its better flexibility would make it more robust for the ICT. When printing, though, the chassis was too rough and fibrous, so we switched to PLA. To determine our needed power supply, we added the approximate power usage for each of the toy's electronic components plus a 30% margin, as advised by Dr. Wade to cover leakage current and various voltage drops. We reasoned that the battery should power the ICT for about 8 hours on a full charge. This would allow enough time for entertaining cats during a typical workday. We compared nickel metal hydride and lithium-ion rechargeable batteries as a power source for our project and selected nickel metal hydride due to its lower volatility and cost. We selected a rechargeable battery because that is the standard for most electronic cat toys today. For our battery selection, we considered 7.2 to 3.6 volt battery packs with similar current ratings. We preferred to go with the 3.6 volt pack, however it was out of stock, and other 3.6 volt packs did not offer more than 1,000 milliamp hours. This would only guarantee powering the ICT for about 3 hours. For now, we decided to go with the 4.8 volt battery pack for our prototype. This pack is a good fit for the ICT with an acceptable weight at just under 100 grams. We employed TI's WebBench Power Designer to design a voltage regulation circuit to accommodate boosting power from either a 3.6 or a 4.8 volt battery pack in case a 3.6 volt pack should become available to us. We employ a switching regulator because of higher efficiency and the reduction in need for a heatsink. We boost the voltage to 5.2 volts, accounting for possible voltage loss over the circuit in order to properly supply enough voltage to power a 5 volt voltage bus. We considered designing and building a battery charger for our project. However, NIMH battery charging is significantly complex. Should we undertake designing and building a charging circuit for our battery, a considerable amount of time would be required. Building this circuit would almost be a senior design project in itself. Due to the complexity of designing and building an NIMH battery charger, we decided to use a prefabricated USB charger with built-in overcharge protection and an indicator light to alert when charging is complete. Our power supply circuit is designed to be switched between 3 positions. The first position allows for battery charging, the second position switches the ICT off, and the third position enables powering the toy through a voltage regulator. Switching for our power supply circuit is realizable with a double pole, double throw switch.
This is the schematic of our prototype. We have the battery regulator, USB and 3.3 volt regulator, an audio regulator, microcontroller, crystal oscillator, and the flash memory for the microcontroller. This is the layout of the PCB. The dimension of this layout is 3.25 inch in length and 2.5 inch in width. We followed the standard of IPC 2221A for our PCB design, and we also ordered the PCB prototype to be printed at JLC PCB. This is the first PCB that we designed to work with the RP2040 MCU. Significant components include the RP2040 chips, flash memory, crystal oscillator, voltage regulators, and feature component pins. Unfortunately, our initial PCB design did not successfully work due to a misconfiguration of some components. This is the final PCB that we designed to work with the RP2040 MCU. Changes made include redesigning the battery connection for fitting and replacing our subcomponents, changing the orientation of the USB connector to fit the board. To test the components of the toy, we decided to use the Raspberry Pi Pico for breadboard testing. The Raspberry Pi Pico also used the same microcontroller as our prototype, hence making it easy for us to transfer our work onto the PCB. These are some of the standards that we apply in our hardware design of our interactive cat toy.
Software design. To make our project successful and fully functional, we need to use an application software and embedded software.
This software block diagram shows when the program begins, it starts by connecting to the Bluetooth device. It then checks to see if there's any input from the mobile application via the Bluetooth. If it does not get an input, it runs the base program's LED pattern, sound, and tail motion. If it does get an input, then it updates either the LED pattern, sound, or tail motion, depending on what was selected in the application. After running either the base program or updating program, it will check if the device is turned off or put on sleep. If the device is not off or on sleep, it will check the application input again. Otherwise, the program will end.
For our application software, we use the MIT Inventor with Bluetooth wireless connectivity. While having difficulty with the connectivity of the HM10 Bluetooth module, we switched from using the Android Studios app developer to the MIT App Inventor to attempt to connect with the iOS compatibility. Unfortunately, this did not work, but we found the MIT App Inventor platform to be more optimal for building our application and decided to use it to complete our project. Our application's graphic user interface begins with a main page that will present the toy, features of lighting, sound, and motion. Selecting a feature will take a user to a feature page. The feature page will offer multiple activation options. The capabilities of our phone application include the control of 3 lights, display options, 3 sound choices, and 3 tail motion patterns. For application standard, these are the standards that will apply to our application development.
The lighting effects of the interactive cat toy will use the WS2812 LEDs. These provide a wide range of RGB color choices. The base model will have one color going down the LED strip, while the application will either have the choice of 3 colors going down the strip or a rainbow of colors going down the strip. To emit light on the RGB LED, it requires some current control to avoid any LED burnout. To avoid this, we must simply implement a 160 ohm resistor between the MCU and the LED strip. Then, using the embedded software, we limit the lighting effects to only use a max of 60 milliamps at a time. The code to the left shows a basic idea of how the LEDs will be programmed. The tail motion of our interactive cat toy will be utilizing a microserver motor to provide the tail wagging effect. The base model will simply move up and down at a steady speed, while the application will give the options of moving up and down halfway to up and down full way at a steady speed, or a quick movement of up and down. An added benefit is that we will add catnip to the tail, and the motion will set off a nice aroma of catnip in the air. The position of the servo motor will be grabbed using the degree method, allowing us to create a wagging-like effect. In between a wag, the code will pause and allow another function to run. The CircuitPython code to the left shows the basic idea of this. The stemma speaker of the interactive cat toy will be able to make many sounds that will entice cats. The base sound will be a small animal chattering. Then, on the application, you can change it to either bells or the crinkling of hay. For CircuitPython to be able to emit sound from the speaker, we have to decode the MP3 file into a static array of numbers. After the MP3 file is decoded, we can play the sound through the speakers endlessly through an infinite while loop. The sensor of the interactive cat toy will establish the ability for sleep mode. This will allow the battery life to last even longer. With no interaction from a cat for a short while, the interactive cat toy will switch into sleep mode. When the cat triggers the sensor will send a message to the program to wake up and continue the base toy LED pattern, tail motion, and sound effects.
Our work distribution table represents how work for our project was shared among our group members. P distinguishes the primary and S the secondary members who are responsible for an area of work within our project. The cost to build the interactive cat toy came in at about $150. The project is fully funded by our group members, with each student agreeing to pay 1/4 of the cost. Our progress at the end of our Senior Design 2 class semester has brought us very close to being at 100% of where we would like to see the interactive cat toy project to be. In the process of completing our prototype, issues arose that left us considering ideal alternative designs.
There are a few ideal alternative project designs that we would implement into our interactive cat toy. For instance, a better placement for the motion sensor, a smaller and robust connection, a better sync with the Bluetooth for less delay time, a switch-off option for each feature, and a smaller and lighter frame for the prototype.
During our senior design projects, we learned many lessons. Designing and building an electronics device from just an idea has been a fascinating and valuable experience. We will be able to take this great experience forward with us into our engineering careers.